So we've been into chapter 14 dealing with chemical and now phase equilibrium. When we deal with phase equilibrium, think of liquid and vapor as two phases, and you'll have an exchange. Some of the liquid will be transferring into the vapor state, and likewise the vapor into the liquid state. If there's an imbalance, then it's not in equilibrium, but at equilibrium the rate at which liquid goes to vapor and vapor goes to liquid is balanced. So we have the Gibbs function. It's made up of how much is in this phase. They use this prime and double prime for maybe the vapor is double prime and the liquid single prime, but it indicates the different phases. So the amount in that phase times the molar Gibbs function plus the amount in the other phase plus its molar Gibbs function is the total Gibbs function for a pure substance having two phases. So that's what the primes indicate, different phases. Now at equilibrium, our criteria is the change in the Gibbs function at constant temperature and pressure, or a fixed temperature and pressure is equal to 0. And also what we just described, how much the rate at which or how much is coming out of one phase is equal to what's going into the other phase or coming out of the other phase. So they're at equilibrium, that has to be a balance, equal to this prime is equal to that prime. You apply the chain rule for this differential change to that function, Gibbs function, and then you conclude that the molar Gibbs function for each of the phases has to be equal to 0. Or we also saw that the chemical potential is another way of describing that molar Gibbs function. So the chemical potential of that pure substance in each phase is equal. This is a problem, and what you would do is, I'll read it. So you use property data for refrigerant 134A straight from the tables, those values in the table, and show that the specific Gibbs function, G bar prime or G bar or G prime, it's either on a molar basis or a mass basis, either one, for saturated liquid and saturated vapor are equal at this temperature of 60 degrees C for that refrigerant. So I've already solved this problem. In the interest of time, I'm trying to cover some material quickly so some people can leave, right? Is that you just go back and forth between a mass basis and a molar basis by using the molar mass. So I can work on a mass basis or a molar basis, but the criteria is that in one phase is equal to the other phase. That's the criteria for equilibrium. All right, but let's just talk about how to compute this Gibbs in the one phase saturated liquid. All right, on a mass basis. So the Gibbs function, refrigerant 134A for the liquid, saturated liquid phase, and the Gibbs function on a mass basis is just H minus TS. It's just like what enthalpy, remember? That was U plus PV. Well, G is H minus TS. So we go to the table, we get the enthalpy, saturated liquid, that's H of F at 60 degrees C. The saturation temperature, make sure and put it into absolute Kelvin. Don't want to put 60 there, 60 plus 273. And then S of F, plug numbers out of the tables, chug, you get a number. This number, negative 22.89, I really don't want to take it beyond 4 digits because the temperature is only good to 3. See that? The temperature, I said 273, not 273.15, right? So that's only good to 3 digits. This value for S of F is only good to 4 significant digits. And I know the enthalpy is given to 5, but at best it's 4 digits. It's probably, I should put the 273.15 in there, and then it would be a little more confident it would be good to 5 significant digits, or 4. I take a look at computing it at the second phase. What would that phase be? Saturated vapor. So H of G minus the same temperature times S of G, get the value straight out of the table. Note you only have 4 significant figures on this one. Probably only give it to 4 or maybe even less. And then you compare these two values, and what you find is, yes, they're comparable, but they're not good to infinite number of digits because the data in the tables are truncated. So it's good to 3 digits, negative 22.8. When you move from a single component to a multi-component, multi-phase equilibrium problem, it gets a little dicey. But what you have is you have the criteria in one of the phases, and then the change in the Gibbs function in the other phase, holding temperature and pressure constant. You can relate that to a chemical potential for that phase for the component A and then the component B summed. So then you have the change. Okay. For equilibrium, it's the same description of moving out of the liquid phase to the vapor phase. For component A, that has to balance, as well as for component B. So that's these two equations. And then you say that the overall change in the Gibbs function, the sum of the for the both phases, that must be equal to 0 at equilibrium. With algebra, you find that the chemical potential for that component in both phases must be equal to the same value, as well as the chemical potential of B, that component lane B in both phases must be equal. So again, a good example is, think of vapor, liquid, and maybe A would be water and B would be ammonia. So a water-ammonia mixture, that's two-phase. Well, now we shift to talk about Gibbs phase rule. Gibbs phase rule just as an equation to tell us how many independent intensive properties we need to determine to fix the state of a multi-component, multi-phase system. So think of P being the number of phases. So if you have liquid only, P is 1. Liquid and vapor, P is 2. Liquid, vapor, solid, P is 3, and we really don't go beyond that, right? So now what would be N? N would be the number of components. If it was pure water, N would be 1. If it was water and ammonia, N would be 2. Water, ammonia, oxygen, N would be 3. So you see how you have P and N. Y, think of Y as a mole fraction. So you could have the mole fraction in the one phase and the mole fraction in the other phase. What is the mole fraction of water in the liquid phase? What's the mole fraction of water in the vapor phase for this multi-phase, multi-component system? Now we do know that if I add the mole fraction of component A plus B plus all the components, if I add them all up, right, there's a little dot, dot, dot right here. They have to be 1, so there's really only N minus 1 independent mole fractions, because the sum over all of them has to equal 1. So there's N minus 1 independent mole fractions for each phase. So you have the N minus 1 mole fractions that describe the mixture in the first phase and then in the second phase. So that's what we mean here. It's N minus 1 independent mole fractions for each of the phases. So if you multiply the number of phases times N minus 1, you get the total number of degrees of freedom to characterize the multi-component, multi-phase system just in its mole fractions. You add to it temperature and pressure, that's 2 more. So you would have 2, 1 for temperature, 1 for pressure. And then you have P times N minus 1 would be the total number of degrees of freedom that characterize that system. Well, we had a discussion of the equilibrium constraints. So we know that mu sub A in one phase must be equal to mu sub A in the other phase. Well, let's say you had 3 phases. Well, then mu sub A in the first phase must equal to mu sub A in the third phase. And what happens if I had a second component, B? That's mu sub B first phase equal to mu sub B second phase. So these are constraints from the chemical equilibrium. And our mixture is going to be in equilibrium. So we find we have N components, and we have P minus 1 constraints for each of those components. See, if you had 3 phases, you had 2 constraints. So P minus 1 conditions or constraints. So the total number of constraints is N times P minus 1. A little abstract. Hopefully you're following this discussion. But what we do is we put it together and we say, okay, for a multi-component, multi-phase, non-reacting system, you have F. I want to know the number of independent intensive properties needed to be specified to fix that state. Well, it would be P times N minus 1 plus 2. That would be the total number of those descriptions to fix the state. This was thinking about the Y's. This was thinking about temperature and pressure. And then you take off or subtract the number of constraints from the chemical equilibrium, the mu, the chemical potential relations. You do a little bit of algebra, and you find that the number of independent intensive property is 2 plus N minus P. That's what you have to or somehow figure out or specify to fix the complete description of the multi-component, multi-phase system. Let's solve this problem. How many independent intensive properties? They're asking for F. What is F? The number of independent intensive properties that are required to calculate the specific enthalpy. If I really wanted to know the specific enthalpy of a liquid solution of water and ammonia, so I'll have not a two-phase solution, but a liquid only. You're off. John, thank you. So P is 1. N, water and ammonia, N is 2. So if I wanted to know the number of F, the number of independent intensive properties, so I'm able to calculate a property like specific enthalpy using Gibbs phase rule, 2 plus N minus P. Let's substitute the numbers. 2 plus 2 minus 1. How many do I need? 3. So for example, if I needed to calculate the enthalpy, it would be a function of what type of 3 things? I have a liquid solution of water and ammonia. Temperature, pressure, and a mole fraction of either water or ammonia. One of them, if one is 60, the other is 40. So they're not. So let's just say the mole fraction of ammonia. You're done. See how you would use that? And then that would allow you to calculate that other property known as enthalpy. This is an application of the Gibbs phase rule. Another application. How many independent intensive properties, that's how large is F, exist for a pure substance in an equilibrium solution with the solid, liquid, and vapor phases present? So how many phases are present? 3. How many components are there? Why is it 1? Because they said it was a pure substance, not a mixture of water, ammonia, or whatever. It could be pure water. It could be pure ammonia. It could be pure carbon dioxide, whatever it is. So you have 3 phases in equilibrium for a pure substance. So let's apply Gibbs phase rule. It's what? You have 2 plus N minus P. 2 plus 1 minus 3. What do you get? Well, hold it. What does that mean? That means if I wanted to know the enthalpy, true, it's a function of what? What's going on here? Is a function of nothing? It's the triple point. So basically, the enthalpy of saturated liquid is just the enthalpy of saturated liquid. It's a number. It's a constant. It doesn't, you specify the substance. It's water, and the triple point temperature and pressure are fixed. I don't have any more degrees of freedom if I said, go give me the saturated liquid's enthalpy. You got it. It's just a number. It's not going to change if I change anything because it's only one point, the triple point. Likewise, H of G for the saturated vapor, the vapor component. And then for the solid, you could use what? H of S is just a number.